All right, on this lovely day, we are going to be continuing solving exponential and log equations. So let's turn to page 3, and we are going to exponentiate. There's a great word right there. Hilarious, I sound so intellectual. We're going to exponentiate each side. In other words, we're going to rewrite in exponent form. If you exponentiate each side, another way to say that is just rewriting the log into exponent form. So it doesn't actually matter which method you do. So let's say here we have log 3 of 2x plus 1, or 3, all equals 3. So let's see what we are doing here. To exponentiate each side kind of looks like this. Notice I have a base of 3 there. So if I make a base 3 on both sides, in other words, this entire log and this small 3 all become exponents. I exponentiate each side. Notice what happens here. This 3 drops with that log, and I now am left with this 2, and let me see if I'll rewrite it down here, plus 3. And notice what this part here becomes, equals 27. So what did I do? Just like on a previous problem, when I had 10 to the 7 equals some 15, or 10 to x, you don't have to write this. What we did on both sides is effectively I just logified both sides and then was able to cancel out. So instead of thinking log, I thought exponent. So I took this base and I made it huge so that this is now an exponent and that's now an exponent. Now from here, we're going to do 2 steps. We can do it all at 1. So I'm going to subtract 3 to get 24, divide by 2 to get 12. So my solution is 12. So let's just double check that work real quick. And now I'm going to substitute the solution into the original equation. So here I get 2 times 12 plus 3. All that becomes 27. And of course, we know that 3 to the third power equals 27. 3 to the third power equals 27. In that case, I rewrote it into log form. 3 to the third is 27. Before we move on from that, I want you to see that this problem right here, when I put the big old fat 3 down below, another way to consider it is just to look at it in terms of a rewrite. I could say this base, 3, to this power, 3, is equal to this number here, or this expression. So I said 3 to the power of 3 all equals that. 3 to the power of 3 all equals 2x plus 3. So I rewrote it from log form to exponent form, which is the same thing as turning this into an exponent and this into an exponent. All right, let's back up and go a little bit easier for a moment here. We are given this problem here. Solve log 7 of 3x minus 1 equals log 7 of 2x plus 2. So, being Sherlock Holmes that we are, we observe and not just see. We observe and not just see. We observe that these are exactly the same. So, effectively, we are ignoring them and focusing our attention on these guys here. So, those two can now be equated, so those drop out, and I bring down the 3x minus 1 equals the 2x plus 1. So this is called the same base property, that since they have the same base, then we can just effectively ignore the logs with base 7. And now I'm going to continue to multiply or add and subtract, etc. So I'm going to subtract 2x from both sides to get x and add 1 to both sides. Well, maybe I'll show the step right there. Add 1 to each side to get plus 3, and then subtract 2x to get x equals 3. So the solution is 3. Double check that, and of course the check can be a mental exercise. When I plug 3 in, I get 3 times 3 minus 1, and over here is 2 times 3 plus 2. All this here is 9 minus 1, so I get log 7 of 8 equals log 7 of, and this becomes 6 plus 2, also 8. So we see that even if we didn't simplify all the way, we do know that they are the same, hence equivalent.
Whoa.
This also makes you sound very intellectual and grown up. The word extraneous. Extraneous. It clearly means, or it means exactly what you think it means, extra, left over. Now, more in particular, not only does it mean left over, but it means that it does not work. Extraneous solution is a mathematical number that you get, a solution that is not a solution. A solution that is not a solution. So, for example, if I were solving a mathematical problem about Pythagorean theorem, bloop, here, and this is clearly not drawn to scale, a 3, 4, and I wanted to know what this is. You do not need to do this. I just want to quickly show you. But remember, this is 3 squared plus 4 squared equals x squared. Mathematically, I get two answers. Mathematically, I get 25 is x squared. So when I take the square root, I get two numbers. Which two numbers? I get x is negative 5 and positive 5. Technically, both of these are mathematical answers. They both work. They both satisfy the equation. If I put a negative 5 right there, I get a 25. It works. If I put a positive 5 right there, it works. So mathematically, both of these work. Practically, what can I not have right here? I cannot have negative because distance is not negative. I cannot have a side length negative. This is an example of an extraneous solution. Mathematically, I get it. Practically, it doesn't work. Okay? So, at times, we may or may not get extraneous solutions, which is why we're checking our solutions. All right, so in this example here, I have log, and remember this is common log on both sides, and that means I have a base of 10 here and a base of 10 here. All right, notice here, since I have the same logs, what am I going to do with these expressions? Again, there's a plus. Discuss. All right, so our product property of logarithms says that I'm going to take this 2x and this 5x plus 15, and I'm going to multiply them together. Yeah. Next step now is my 2x is down here, and I bring down the 5x plus 15. They multiply together like this. Now, that is going to, I will rewrite that in a moment using the distributive property. But I am going to exponentiate the sides using a base of 10. Exponentiate each side using a base of 10. So remember, make a big fat 10 there and a big fat 10 there. So what happens here? The 10 and the log drop out. So I can bring down the exponent.
Where'd you get the 10?
The question is, where did I get the 10? And it's implied right there. Because this is the common log, the base is 10. So we don't have to write it when it's a 10. And that's from whence the big number comes. All right, so now I have 2x times 5x plus 15 all equals 100. Because 10 squared is 100. Now we have a quadratic equation. So if we can go back to our quadratic equation days, I'm going to distribute here and then put it in standard form. So this becomes 10x squared plus 30x all equals 100. And standard form says I'm going to bring everything over to one side and make it equal to 0. And that should be a subtract 100 equals 0. So now we're in standard form. Let me go ahead and rewrite this. Notice that I can divide each of these guys by 10, and I will do that real quick to get x squared plus 3x minus 10 equals 0. Now I'm going to factor that using my Snowflake method. Remember, the Snowflake method says this. I'm going to take my a times my c, so I put a negative 10 there, and I'm going to put my b on the bottom, and I can put my ax on top, so 1x and 1x. So I find two numbers that multiply to a negative 10 and add to a 3. Again, finding the factors of negative 10 that add to positive 3. And we end up seeing that we can get a 5 and a negative 2. So here's one factor, x minus 2, and here's one factor, x plus 5. Now, I kind of ran out of room here, I'm sorry. So that splits up into this, x plus 5 times x minus 2 equals 0. So I can split those up using the zero product property. So x plus 5 is 0, x minus 2 is 0. So x here gives me negative 5, and x here gives me positive 2. Now, in the end, and because we're hasty, we say, hey, we're done, yay, we're good to go. Dun, 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 dun. The problem is we have to double check to see if there is a mistake. So I'm going to clean up here and check my work over here. So I'm going to rewrite the problem. So log 2 negative 5 plus log times 5 times negative 5 plus 15 all equals 2. So here I get log of negative 10 plus log of negative 25 plus 15 equals 2. And continuing here, notice that all of this, log of negative 10 plus log of negative 10, all equals 2. And we should actually have question marks there. This here becomes log of negative 10. And now, of course, at this stage, you probably would have recognized, or at any of these stages, you probably would have recognized, that there is no exponent. Remember, there's a hidden 10 right there. There is no exponent on a 10 that'll give me a negative 10. Because remember, 10 to the negative 1 does not change my base to a negative. What it does is reciprocates my base. So notice the sign is positive here. The sign is positive here. There is no exponent that'll change my sign from a positive to a negative. So I can't clean this up. Even if I tried to cancel this stuff out, I still have a negative here, which now becomes negative 2, which clearly negative 2 does not equal positive 2. So what do we conclude? That although mathematically I get two answers, this one is not one of them. Only x equals 2.